This video, we will be introducing Gibbs free energy as well as calculations that involve free energy. We have seen examples of endothermic processes that are spontaneous. So ice could melt, or when you dissolve ammonium chloride in water, the temperature decreases. So both of those are endothermic processes that occur spontaneously. If that spontaneous process is endothermic, something else must accompany it to increase the entropy. So we have to have two things like we've talked about in order for something to be spontaneous. The spontaneity of a reaction involves both enthalpy and entropy. So if our endothermic process is spontaneous, then we're also going to have to look at entropy to see how that is a spontaneous reaction. That is what we use Gibbs free energy for. So what we're going to focus on in this video are three different methods to calculate Gibbs free energy. We're going to use a relationship that we're going to look at between free energy, enthalpy, and entropy. Then we're going to use tabulated values of the free energies to calculate delta G directly. So that's like we did with delta H and delta S. Just calculate it from the values in the appendices. And then the final method is going to be to determine free energy in a stepwise reaction, like we did with Hess's law. So we're going to look at each of those three calculations as well as what free energy means. With Gibbs free energy, a scientist by the name of J. Willard Gibbs proposed a new function, which was represented by the variable G, now known as Gibbs free energy. This function, this free energy variable, connected both enthalpy and entropy. The change in free energy for any process can be represented by this equation. Okay, delta G equals delta H minus T delta S. That is on your equation sheet, and that is going to be a very, very common equation that you're going to use. So you definitely want to make sure that you know how to use that. In that equation, delta G is the free energy, delta H is enthalpy, T is absolute temperature, so it has to be in Kelvin, and S is the entropy. The whole purpose of using this free energy is that the sign of delta G gives us extremely valuable information about the spontaneity of the process that is occurring. It's much more convenient to use Gibbs free energy rather than entropy because when we're focusing on delta G, we're only focusing on the system. And so delta G is going to be much more useful than focusing on exothermic endothermic reactions as well as decrease in entropy. Something to know is that in any spontaneous process, free energy always decreases. Okay, so this goes along with this yellow box. If delta G is less than 0, okay, if delta G is negative, a reaction is spontaneous. So this is similar to delta H. Delta H is less than 0, it's exothermic. Okay, well, if delta G is less than 0, it's spontaneous. If delta G equals 0, it's at equilibrium. So at equilibrium, delta G equals 0. And then if delta G is positive, it is non-spontaneous. What we're going to use in terms of the word spontaneous is you might see it say thermodynamically favored. Okay, that is the same thing. They're just using different terms now. So instead of something saying it's spontaneous, it might say that it's thermodynamically favored. That's going to be the same thing. So taking a look at this graph, this is a reaction of nitrogen gas and hydrogen gas at equilibrium with ammonia. Free energy always decreases in a spontaneous process. So notice that both directions are spontaneous depending on where you're at equilibrium, but when it's spontaneous, free energy decreases. And so the free energy gets progressively lower and lower as the reaction moves toward equilibrium, which is this spot right here on the graph. The minimum on the graph, that is equilibrium. Okay, minimum in free energy means that you're at equilibrium because remember, when delta G is 0, you're at equilibrium. The second way is to use the standard free energy values. Okay, and so to do that, it's going to be similar to what we did with entropy. But before we get into that, it's important to know that delta G is a state function, okay, just like delta S and just like delta H. Okay, they're all state functions. They only depend on the initial and the final state. And so because it's a state function, we're only going to focus on products and reactants. So the equation that we will use is this at the bottom. Delta G naught of reaction, so the standard delta G of the reaction is equal to the sum of the free energy of the products minus the sum of the free energy of reactants. However, unlike entropy, delta G for any element in its most stable state is 0. Okay, So what that means is whether it is diatomic or not, if it is in its most stable state, so Cl2, Br2, Na, O2, okay, it's 0. That's the same as delta H. Okay, delta H is the same, but entropy is not. Okay, so as you go through, if you're like, well, how am I supposed to know the delta G for O2? Well, it's 0. Okay, so this equation is also on your AP sheet, so you can use this, but now we're going to look at some calculations using this equation instead.